Hi everyone, thanks for your warm welcoming. So I'm Hugo Crochet, I'm the Chief Information and Data Officer at CLB, and I'm here with Quentin, who is a data scientist specialized in natural language processing. And today we are going to see how we use data for AI for a very specific task, which is data structuring, and how we use it for research and cancer treatment. First, a few words about Berard Cancer Treatment Center. So we are based in Lyon. We are 100% dedicated to cancer treatment and research. So we are basically an hospital plus a research center on the same site. Here is a quick picture of how it looks like with the big hospital on the lower part and the research buildings on the top part. And we are more than 2,000 employees following more than 40,000 patients a year. So quite a big cancer treatment center for France. We have been invested in cancer real-world data for quite some time now. We have a dedicated data team that we created in 2021, and we are now 10 people today, and we think it's the minimal size that we need, so we're pretty happy about it. We've been investing in a tool that's called Consor, that we're going to talk more about later, and it's a tool that is helpful to structure data and to make research on data. And it is a tool that has been built by Unicancer, which is the national federation of the 20 cancer treatment centers in France. We are very proud to be working with some of the most well-known startups and academics in AI and data structuration in France. Some of them, some of the logos are here, and we are also very invested in data sharing projects, working a lot with the French Data Hub, and working also with a lot of European projects to do a lot of data sharing projects, either federated project or centralized projects. So if we dive into a little bit into the world of data in a cancer treatment center, we have 200,000 patient files with a cancer. And all of these patients have multiple types of data. I will start with the more complex one and the most recent one on the right, the omics information. We have more than 50,000 patients sequenced. Most of them, or almost all of them, have pathology blocks that have been analyzed that we can use to sequence data, to extract ADN and extract omics information. All of them have medical imaging, either MRI or scanner, and all of them have clinical data. And most of the clinical data, around 80%, is in the text, in the free report that has been written by the physicians. And basically, the topic of today is trying to transform these 18 million documents into something that looks like an Excel file, that is a structured format that we can use for research. Just to explain a bit more what is structured data, so we are we start with the medical report that is a free text. Here the conclusion: right breast upper outer quadrant core biopsy, invasive carcinoma of no special type, SBI grade 2, ER3+, PR3+, HER2. So if you want to use this, you can't use it like this in research. It makes no sense. So you have to first structure it in a semi-structured format. So you're basically extracting data from the sentences in some broad categories, cancer type, site, grade. And then the second step is to structure it. So you are normalizing it on international referential. So for example, you move from cancer type breast invasive carcinoma to a localization code, C50.4, and a morphological code, which is there. So there you have structured data, but there is one final step that is the hardest one. It's to know which cancer you're talking about, because unfortunately, 12% of patients have multiple cancer. And when you are reading the text, if they have multiple cancer, you don't know which cancer the clinician is talking about. So you need to infer that, and that's a very complicated part. So once we know what data structuration is, let's see how we use it. So we are using it in the orange box in the middle with Consor plus internal NLP. And once we have the data structured, we do three things. The first is what we identify cohorts for research to include people, patients in clinical research or to do data sharing projects. Then we export data for data sharing projects. We are also working on automatically filling ECRF for collecting data. That's more on the research side, and on the clinical side, we are sending back all the structured data to the EMR, So it makes it easier for the clinician to structure data. They just have to validate. So there is like a suggestion made by the AI, by the data structuration tools, and they just have to validate. Just a quick view of the console interface, the tool I was talking about. Here we have a research. I want all the patients that have that are more than 18 years old at diagnosis after 2012, that have metastasis, but not metastasis when diagnosis. So you see, it's a bit tricky to understand. And then you have prostate cancer, people with PET scanner, and you want to have the report of imagery, and you want that in the report. They are the words adenomegaly or adenopathy. And you find top right corner 226 patients. And when you hit the button, see the patients, you get a synthesis like this for each patient with all the cancer, if the patient has multiple cancer, and all the status and all the treatments for this patient.
So to achieve all the wonderful things my colleague exposed here, we need to use the right tool. And the right tool for that is NLP. NLP is not a very new technology. It can trace it back to the 50s, so quite old for me. It comes with several important milestones through the years. For the example, in the 70s and the 80s, the lexicon system, and more recently with the transformer architecture model, like Berard, for example, and the one we are here to talk, the LLM part in 2023. But despite all this new technology and model architecture, we have several challenges to work with when we work with text, and more importantly, in our case, medical text. We have a diversity of format and medical language. I think you all know what I'm talking about. A medical report can be written in a challenging way, I think, could word it. We have the data privacy challenge. For easily shareable data, like Hugo talked at the beginning, we need to anonymize our text, and it's a challenge which is not addressed at the moment. We have the medicine evolution. In our context, we have an old EHR, like 30 years old maybe. So an information we can found in a report 15 years ago can be not true at the moment or outdated. Another challenge can be the need to annotate data for deep learning and supervised learning. So when we build an AI, we need to provide some annotated data for some models, and to have the resource and the technical resource and human resource to make it can be a challenge for hospitals. And most importantly, the bias. Our text just represents our hospital population. When we want to generalize our model, it could be a difficulty for us.
So we are going to go through a practical example. We are going to look at how we are structuring biomarkers from pathology reports. So a biomarker is a biological description of the illness. As you probably know, nowadays we are not talking about breast cancer anymore. We are talking about triple negative cancer. We are coping with breast cancer who responds to estrogen or progesterone, which is ER and PR, and from cancer who produce a protein HER2. And depending on those biomarkers, you have a various survival rates. The worst case scenario is if you have a triple negative cancer with a very bad survival rate. So we understand that it's very important for us to structure this biomarker. It's both important in routine clinic because you want to know what biomarker your patient have, and you want to have it in research because you want to select the cohort you want based on biomarkers.
So how do we address this use case? There are multiple approaches call back to the milestones I'll talk in the histological praise. So you have the first approach, which is the regular expression. It's a rule-based model. Just simply, if I see this word, then the expression is good or it's positive. You have the example in the simple expression case, HA2 positive, comma 3 plus. You can see the pros really rapidly. It's very easy to put in production, and it can make a good performance in simple example. But the cons are also obvious. If I change in the pattern, for example, here in HA2 colon positive, I change the colon and I set a comma, for example. The pattern does not match, and the sentence is not validated, and we cannot structure using our regular expression. So you can say, if we take all the possible pattern, maybe we can achieve a system we can track all, but it's not something realizable. For example, we need to track every biomarker. We have hundreds of them at the moment, and a new biomarker can be published and tracked down via analyze through the years. So we need to maintain the lexicon. It's not something that we want to make at CLB. Our second approach is currently our production approach. So it's using deep learning with BERT model, so transformers model. We take an open source French language model, which is Camembert, implemented by Enria. I say the name is quite fun already. Sorry. And we built Encobert, which is a Camembert fine-tuned on 3 million CLB clinical document. We focus only on the clinical document, which is relevant for our case. We need to structure clinical data. One of the cons of this approach is that we need more annotated data, which is one of the challenge I talked at the beginning. So despite these cons, we have a more flexible system than the rules. Our model can select in the text the biomarkers and interpret their expression. So we have the biomarker and the expression with one model. And we just need some GPUs for the training part, and that's it. And we have a more flexible model, and the performance are similar or maybe more than the rule-based system. It's like a broader system. But even if BERT is our currently production approach, we constantly aim to expand our performance. So we need to get interest to the latest trend, I think, the large language model. So what we hope to achieve, because it's not really a work that we have in the center at the moment. So I think it will not replace Encobert for the classification. The biomarker is mutated or non-mutated, but we can achieve a better understanding of the text and especially more precisions. As I say, BERT model needs annotated data, but LLM does not need it. And we can ask more questions than just where is the biomarker and which is the state. So I think we can have more precisions and better normalization with using an LLM. But is LLM always the answer? Maybe I will be the devil advocate on the GenAI trend of this conference. But even if it has a really big pros for us, like we don't need to annotate data, which is very time consuming with the few shots or the zero shots learning approach. Despite that, we have a very important concerns about the comparison with BERT. We have here a nice illustration of the comparison between BERT model and LLM model on medical comprehension benchmark, in a more precise, with questions needed a more deep understanding of the context. LLM is less performant than BERT because BERT is specifically trained for address this question, which is understandable. The LLM maybe have a broader range of questions, but is less performant on the specific questions. And we have also the risk of hallucination, which is can be blocking in healthcare, I think.
As a conclusion, that as you've seen, we think that there is not one solution that fits it all. We think when you have an LP task, we use multiple tools, and that's the most efficient way. And what we try to keep in mind at CLB is kind of AI frugality. So if we can do something that works with a rule, why would you use an LLM? It's just going to cost more resources and take more time. So that's what's guiding us all the time. And as a more an opening view, we are quite confident and optimistic about the future because of you see on this little graph, NLP in healthcare and AI in healthcare is a very trendy topic, and we think the situation is evolving very rapidly. Thanks for your attention, and we have a few minutes for the questions.
Thank you.
Thank you so much. Please raise your hand if you've got questions. We've got a few minutes. Don't miss out.
Thank you for the presentation. I have one question about your training. So how many classes did you say you have, and how many label sample do you have per class for your training of Camembert?
So for the using of Camembert is used only as a foundation model. So we take the Camembert and we apply a strategy as continuous pre-training. Like we train the foundation model. Encobert is a foundation model. Then we fine-tune it on the biomarker detection case. In this case, we have indirect tasks, which is a track where the biomarkers are in the text. And then it's classification tasks with 4 states for the biomarker: positive, negative, don't have any information, and like a specific task for one biomarker on the breast cancer HA2, which is an ambiguous state. And maybe 10,000 sentences as a training set.
Hello. So how will it be possible to access this data and tools outside of Léon Berard? And would you think of using federated learning to do this at the level of Unicancer?
Yeah, so it's very hard to share the reports themselves because they are very hard. It's very hard to guarantee that they are 100% pseudonymized. But we have already shared the model with other cancer treatment centers, Gustave Roussy, Lille, and also France. And they have tried it, and we are pretty happy because the results were consistent. So it means that we are generalizing quite well. And the next step is to install it in Consort, the national tool, and so every cancer treatment center can have it. But yeah, we are working on another project with the Health Data Hub, and we are trying to build a federated platform to be able to circulate those models. And we are also actually working with the French regulation, the CNIL, because we want to publish it publish Encobert, the model, open source, which is I see you nodding. So yeah, it's a big topic, but we think there is a space here, and maybe it's going to pave the way for more sharing. So we are very conscious about data privacy. So we are looking at things very closely and working with research teams to make sure that it's impossible to go back to the patient, but still we are thinking it could change things if we could share this model more efficiently and more fluidly.
Would you like to share a bit about the process, how long it took you to put the first model together, the second model?
So the entire process took about 2 years to have 2 tools. We present you the biomarker tools, but we build another on the toxicities, which is a secondary effect of chemotherapy treatment. So which is, took us 2 years, and the biomarker is the only one currently in production. And we hope to have, we start from scratch, so we need to build, need to build a lot of pipeline or some groundwork, so I could say. So I think the next subtask could be more efficient on the production.
Any final words you'd like to share with us?
Come to see us at our booth if you want to talk
Where
about
is your booth?
The big one with Curie, Institut Curie, and Université Onkobo on the left.
be sure to go find them. And thank you so much for your talk. Thank you.
Thank you.